Okay, so for the do now, I want to review types of solids, and then I'm going to put up a table that's from the notes, just to make sure that you've got the different types of solids down. In terms of types of solids and what you need to know from chapter 12, it's just conceptual. So you just need to know how to identify different types of solids and properties that they exhibit, which you'll see in mastering as well. So for 1 through 4, you're just matching the type of solid with its predominant force. So number 1, if we look at metallic solid, we're just looking at which of these 4, and we're just going to use each of them one time, which of these 4 best describes metallic solid. So based on the notes, which of these would best fit the metallic solid?
Sea of electrons?
Sea of electrons, yeah. So 1 is B. So metallic solids exhibit properties like they're conductive, they can be drawn into a thin wire, so that's ductile, they're malleable, they can fold easily. That's because of the sea of electrons. So the electrons are not just stuck in one place like in other types of solids. Instead, they can move around. And so since you have electrons that are able to move around, that gives the metallic solid a lot of the properties that they exhibit. Alloys are types of metallic solids as well. I'll talk about alloys on the next slide. But we have different types of alloys that exist really all around us. For number 2, ionic solid. So which of these, so we've used sea of electrons. Which one of these would best describe ionic solids? Ionic bonds, right? So ionic solids like NaCl exist in a crystal lattice. And an ionic bond, and the term bond is not quite accurate, but it's called an ionic bond. It's actually an attraction between a positive and a negative. So for example, I had the NaCl like magnets. So these are really strong magnets. I have Na plus, Cl minus. That attraction is an ionic bond. And so if I put a lot of these NaCls together, it would form a crystal lattice. So ionic solids exist in crystal lattices held together with the electrostatic attraction of ionic bonds. Covalent network solids. So there are only a couple covalent network solids, and these are very unique. Carbon, so diamond and graphite, are examples of covalent network solids, and SiO2 is another example of a covalent network solid. There are only a few. Everything else would be considered molecular. But covalent network solids are very unique because they have very strong properties. So diamond, right? Diamond is very, very, very hard to break. And that's because of the unique properties that exist because of which of these 2? It's a covalent network solid. Covalent bonds. So covalent network solids are held together by covalent bonds. So instead of being held together via intermolecular forces, like molecular solid being like water, solid carbon dioxide, covalent network solids like diamond, graphite, silicon dioxide, they are actually held together by additional covalent bonds. So that gives it an extremely high melting point. Very hard, like they have very high like hardness levels because of those covalent bonds. Molecular solids are all nonmetals, so it could be an atom of a nonmetal like argon or xenon, N2 gas, or I guess instead of gas it would be solid nitrogen. Those are molecular solids, so anything else that is all nonmetals would be molecular solids, and those are held together via intermolecular forces. So ice, right, solid water, its strongest intermolecular force would be hydrogen bonding. But something like solid CO2 would be held together with dispersion forces because that's the only IMF that would exist. Oh, I just gave up both of these. Okay, well, right, CO2 will form a molecular solid. When you have all nonmetals, it will form a molecular solid with the exceptions of carbon, whether it's graphite or diamond, and SiO2. Those are, and then sometimes SiC, so silicon carbide. Those are the only covalent network solids. So the only ones that are listed in your notes are the only ones that you have to know. So if it's not one of those exceptions, which is a covalent network solid, a covalent network, and it consists of all nonmetals, then it's a molecular solid. Now metalloids, like Si, Ge, arsenic, antimony, they could exhibit properties of either nonmetals or metals. It's all dependent. That's kind of the definition of a metalloid. So I will go over solids again on the next slide, but before I flip to the next slide, a couple things. You will have some time today to work on the post-lab and mastering. But for those on Google Meet, or if you guys know of anyone that's in the green group or that's online, now that we are online next week, in the top tray is the chapter 13 notes packet. And then on the counter is the do now sheet. I'll talk more about the do now sheet in a second, but you want to make sure, like for you, you pick up both of those. If you know someone that's in the green group or online that might want you to pick up the notes for them, or if you're on Google Meet and someone is in class, it might be useful to just grab the notes for someone. So you can like text them. You can always come back later in the day and grab them. But it's like 10 pages front and back. I mean, so if you print single side, it's 20 pages. So it's a lot of printing. So that way, if you're at home and you can even like put it in somebody's mailbox, you don't even have to like see them, just put it in their mailbox, text them and be like, hey, your notes are in your mailbox. But that way it just might be useful. That way you have them and you don't have to worry about printing them out. The do now sheet, could be a little bit easier. You could do it on a piece of paper or something, but the notes might be a little more difficult. So that's just something, because you will want both of those for Monday. So I'm going to go to the next slide, which has more on the types of solids. Now this table is actually on the front page of the chapter 12 notes. So this is nothing new. This is on the front page of the chapter 12 notes. And it has the different types of solids. So molecular, covalent network, ionic, and metallic. Something that's important to remember is that alloys are types of metallic solids. So you have heterogeneous alloys, you have substitutional alloys, and essentially the difference is just the size of the particles. If they're the same size, right, it's a substitutional. And then you have interstitial as well. Right, so if the metal particles are the same size, you're substituting one in for another. That's a substitutional alloy. If you're putting something into the holes of the metallic solid, like stainless steel, you're putting carbon, you're filling in the holes of the metallic solid with carbon. That's an interstitial alloy. So just knowing the difference between the two, usually we see multiple choice questions on interstitial versus substitutional alloys. But this shows the types of solid, their properties. It's very common to see multiple choice questions that will give you a list of properties, and it will say, which would you expect this solid to be? Now, one that is going to be extremely important is that when you have an ionic solid, so you have something like NaCl. And I have a conductivity, maybe Campero has it, but I have a conductivity tester that's essentially two metal prongs connected to a light bulb. If I just stick that into solid NaCl, that's not going to conduct electricity. So table salt is not going to conduct as a solid. But if I dissolve that in water, or I melt it down to a liquid, if it's either a solution or it's a liquid, ionic will conduct. So that's a very common property that we see when we're trying to determine types of solids. And you can see, melting points or boiling points. Ionic solids are also hard and brittle. Covalent network solids, this is, imagine like diamond. Diamond has an extremely high melting point. It's very hard. That's because of the covalent bonds. And then metallic, They are very, very good conductors of electricity as solids. Everything else, molecular covalent network doesn't conduct very well. Ionic doesn't conduct as a solid, only as a solution or as a liquid. But metallic solids will conduct as solids. So again, this is on the front page of the notes, but just to kind of go through, be able to identify different types of solids. You're given something, like CO2, can you identify what type of solid that is? Or, aluminum, NaCl, examples like that. And mastering has you do that as well. Are there any just general questions on types of solids right now?
I think there's one I'm mastering about aluminum. Do they have to give you like how do you determine if it's?
So if it's just like solid aluminum, or like just Al on its own, like atomic aluminum, even though aluminum technically touches the bold line, aluminum is a metal.
Oh, okay.
So imagine like aluminum foil, right? That's a metal. That's the only one that touches that bold line that's not actually a metalloid. So aluminum just exists as a metal. Any other ones that touch that bold line on the periodic table, those would be metalloids.
And then how would you determine what the metal is?
So then you would just have to look at properties that they would give you.
Oh, okay.
But like SiO2 is a common one. Well, that's a covalent network solid. But sometimes it would just depend on properties at that point. They would have to tell you, it either has, it's hard and brittle, or it has a low melting point, and then you could kind of go based on those properties. Yeah.
Can I take a picture of this one?
Yep.
It's in your thing.
Okay. Oh, it is?
Yeah.
Yeah, front page of the notes, but it's okay.
Better on here. Thanks.
Okay. So before we actually get into work time, I want to talk about separating liquids, and I want to focus on chromatography to hopefully answer questions that you might have for pre-lab or post-lab. Because the lab does ask you about what it means about attractions to the paper or to the solvent. So I have this link up here is the link to these slides. So if you'd rather just have the slides open on your Chromebook, you can save them to like an AP Chem folder. So it's just bit.ly/33W3GZB. And I have it on like the first 3 slides. And let's see if I can send this to you guys. I know it's hard to see. 3, wait, I can just copy it. It'd be better if I just copied it. We're fine. Fine. All right, so for you guys on Google Meet, I just sent the link so that you have these. This is kind of an extension to chapter 11 because it still talks about intermolecular forces. So I'm just going to briefly talk about the 2 ways that we separate liquids. So when it comes to separating liquids, if you think about ways that we've looked at separating things so far, we've filtered. So you can filter substances. Now, if I try to filter a mixture of 2 liquids, it's probably not going to do anything. Because when we filter, we want something to remain in that filter paper. So we filter when we have a mixture of solids and liquids. If we have liquids and solutions, so we have a mixture of 2 liquids or 2 solutions, we can't separate them using filtration, and we can't separate them using spectroscopy, which we'll look at when we get into kinetics. Because these separate by the size of the particles, and liquids are mixed together. So 2 different ways that we can separate liquids are chromatography and distillation. So we've talked about distillation before, but chromatography is where I want to spend some time looking today. And again, these slides, I have the links kind of up at the top, so you can just have those open, or you can always go back and refer to them. They're actually in the Do Now slides as well. So these are actually just an extension of the Do Now slides. But if you go to this link, I've created a separate slide deck. So for chromatography, and a lot of this is in the background information of the lab for chromatography, but when it comes to chromatography, now that everyone has been exposed to chromatography, it'll make a little bit more sense as I talk about the paper and the stationary phase and the mobile phase. So all chromatography, no matter what kind, and I'll talk about two different kinds, involve a mobile phase and a stationary phase. So mobile means it moves. Stationary means it stays still. So for our paper chromatography that we did in class, the paper was the stationary phase, and the solvent that moved up the paper was the mobile phase. So in lab, we had the paper as a stationary phase, and for us, our solvent was an NaCl solution. It was a small amount of NaCl dissolved in water. So when the solution is exposed to the mixture, each part of that mixture will have some sort of affinity or attraction for both the stationary and the mobile phase. So if you did the unknown in lab, you saw that there were 3 different colors of the unknown, and they actually separated out. If you actually looked at it initially, it was kind of a purple color. And then as it started to move, you notice then it was kind of a green color, and then it actually spread into 3 distinct colors. And that's because every dye had a different attraction to the solvent and to the mobile, or to the paper. So when it comes to paper chromatography, so paper chromatography is also known as thin layer chromatography. We just refer to it as paper. As we look at the chromatography here, so this looks somewhat similar to what you guys did. We did it in test tubes instead, but we had the ink spot that was above the solvent. The importance of having that ink spot over the solvent is that way it moves up the paper and it doesn't disperse into the solvent. Because then you're not going to have an ink spot that goes up the paper, it's going to be in the solvent instead. And then it slowly moves up and it separates the components based on the attractions. So if one of the components of the mixture has a high attraction to the mobile phase, so to the solvent. So let's say that I think the blue colors moved up really far on the chromatography papers. If the blue moved up really far, that means it was attracted to the solvent, because as the solvent moved up, it was attracted to the solvent and it kept moving with the solvent all the way up the paper. If the component is more attracted to the paper, right, so it's less attracted to the solvent, more attracted to the paper. As the solvent moves up, and let's focus on like this first spot. The solvent's moving up, it's moving up. Well, the dye is actually more attracted to the paper, so it's going to stick to the paper. So even though the solvent's moving up and up and up, if the dye is more attracted to the paper, it's not going to move as far. So it's all about polarity. It's about the attractions to either the solvent or to the paper. In our case, the solvent was an NaCl solution. That's an extremely polar solution. So the farther up the dye moves, we could say the more polar it is, because there's similar attractions. The paper is only moderately polar, so the paper is technically more non-polar than the mobile phase, than the solvent was. So the different distances, if you notice that you have multiple colors, that means you have a mixture. And that means that the mixture separated fairly well. Now your calculation within the lab is calculating the RF value. So we can apply kind of a quantitative aspect to chromatography by calculating RF, which is rate of flow. So the RF value, and you did it in the pre-lab and you'll do it in your calculations, you're looking from where the ink spot was placed to where it traveled. From where it was placed to where it traveled, and we always measure the center. We compare that distance to the distance that the solvent traveled, which is from the line up to the solvent front. So the higher the RF value, that means it traveled up further, because you have a larger number divided by solvent versus a smaller number divided by solvent. So the higher the RF value, the further it travels on the paper. The usefulness of these RF values is you will be able to take your unknown, the 3 colors that were in your unknown, and you can actually compare those RF values to the RF values of your known samples. So you had 7 known samples and 1 unknown. You can compare those RF values to the 7 dyes, and then you can actually see which colors they were. Now, there is one other type of chromatography. So paper chromatography is usually best used just as a way to analyze if we have a mixture or not. The only thing that we really do is separate. If we want to actually collect liquids, let's say we have a mixture of 2 liquids or the mixture of 3 dyes, and you want to actually collect each one individually, we have to use what's called column chromatography. Now, these are very expensive to put together, so we don't have column chromatographies, or I should say we just don't have the columns because it's actually different substances. So sometimes you'll have like kitty litter, and you'll have silica gel, and you'll have cotton, and then you have this special solution that it gets mixed down through. And so we use column chromatography if we want to isolate and separate and then recollect the liquids. So if you want to actually collect the mixtures within the liquid, we would use column chromatography. This is actually what it would look like. So you put the sample into the top of the long tube, and then you have a mobile phase, and it actually works its way down through the column. So it'll work its way down through the column, and then you'll be able to collect each one individually because they move at different speeds because they have different attractions. So essentially the usefulness of column chromatography, if there's one thing you take away from column chromatography, it's that if you want to collect the liquids in the mixture, you use column chromatography. Right? We can't collect the dyes off that paper. You can't just pull the dye off the paper. So it's a good way to separate, but if we want to collect, we would use chromatography. Now, just a quick review of distillation. I'm not going to read everything on the slides. You can go back and you can review these slides if you don't remember distillation. But distillation is a way that we separate liquids or solutions based on their differences in boiling points. So the most common example is ethanol and water. Water has much stronger intermolecular forces, giving it a higher boiling point than ethanol. Ethanol has a lower boiling point. That's because of weaker IMFs. And so this shows the distillation setup. I have a mixture of liquids. As we're adding heat, boils the liquids. The one with weaker IMFs boils off first. It actually, up here at the top, this is sealed, so it can't escape. So it goes down this tube, and there's cold water running around it. And because it's cold water, it condenses the liquid. So it condenses that gas back into a liquid, and then we can actually collect the liquids. So if you want to separate mixtures, common example, I'm recording, well, that's fine. Common example is like an alcohol still uses ethanol to purify alcohol. Because what you can do is you can actually boil off the ethanol, which has a lower boiling point, collect it, and then you're left with the water and the purified ethanol. So that's exactly how a still works. And it's all based on the intermolecular forces. So again, this is just looking at IMFs. It's essentially taking you step by step through how distillation works. But distillation is based on boiling point. You're separating liquids based on boiling point. The one that boils off first is the one that you'll collect first as a liquid, and then that leaves you with the other liquid still in the container. All right, so now you guys are just gonna have time to work for today, and there are a couple different things. I'll leave this up so that way you can refer to it as needed. Hopefully you already watched the chapter 12 videos, which was all on the different types of solids. Mastering, so chapter 12 mastering, it's not technically due until Friday at 11:59 p.m. but should not take you very long. I think some people said it took them about a half an hour. And it's 13 points with 3 points bonus, so you can get up to 16 out of 13. You can use your notes. I've linked the sections of the e-text as well if you need those. But make sure you've watched the videos before you work on mastering. If you'd rather work on post-lab, like with a lab partner with a small group, you can work on the post-lab. So you have pre-lab, we have purpose, procedure, pre-lab questions, right? That's your pre-lab. Then your data and observations will really just consist of the data table. So make sure you label and title it. So like data table 1, distance values, right? Something like that. And then you have your picture of your strips. So that will just get like attached to Google Classroom as well. But if in your lab notebook you want to write, see picture for strips, you can do something like that as well. And then calculations. So your calculation section will just look like this. So you'll have calculations. And in the lab, it tells you have to show one sample calculation. So you label your calculation. So you're calculating RF. And then I'll just show my work for one sample calculation. RF is distance of the dye over distance of the solvent. Show your work for one, that's it. All of the rest of them just go into your data table. You do not have to show every single calculation. And then post-lab questions and conclusion. There is no data analysis. So conclusion as purpose, did you fulfill it, why or why not? So short. Post-lab questions ask you about interactions and sources of error, what's the unknown, things like that. That's due Tuesday morning in Google Classroom. And then make sure you do pick up the Chapter 13 packet and the Do Now sheet. If you know that there's anyone on Google Meet that might want you to get it for them, send them a text, ask them if they want you to get it. You will actually turn in your Do Now sheet. So like this week, today is actually the last day of the Do Now sheets because Thursday and Friday there's no school. But because I'm not going to see the green group for a week, I'm actually just going to have everybody turn in your Do Now sheets via Classroom. So you'll notice in Google Classroom, there's a new assignment that says Do Now sheet 1125. So you can just write none or no school under Thursday and Friday, and then you'll actually just take pictures and upload it to Classroom. So just get that done at some point today. When you do it is up to you, but then I'll just go through and I'll grade them that way. So that's it. I'll leave this up so that you can refer to this as needed. If you have questions while you're working, I'll answer questions, but what you want to work on is up to you. You can move around, and so what? We have until 8:20. You have a half hour, 8:29. And for those of you on Google Meet,